So our assumptions here, in order to have the central limit theorem kick in, we do need one of these two things, either independence, if we're talking about sampling from something other than a population. If we're sampling from a population, then it's a simple random sample, right? So these two things go hand in hand. We also need our sample size to be no larger than 10%, same reason that we had in part 6. So nothing here is new. Our rule of thumb is slightly different than it was in part 6, though. This is our only real change. Now, instead of NP and NQ being greater than or equal to 10, which was the part 6 rule, we just have N is greater than 30, or our original distribution was normally distributed. So if our original distribution is normally or approximately normally distributed, we don't need the 30. We can have a sample mean distribution of something as small as 2. But if we don't have normality or we don't know what's going on, we need 30 to make sure we can see that nice pretty histogram that's normal, like I had in those the last video with the StatCrunch. Okay, so let's do an exercise. So as a reminder, this type of question is just like the questions from 6.1. On the exam, there'll be a part A, which asks you for the distribution, and then a part B that asks you for a probability. So this one's a little bit different than what you'd see on a test, but it's here to demonstrate a very important concept. So in engineering, weights of people are considered so that airplanes and elevators aren't overloaded, chairs won't break, and other embarrassing things won't occur. Men's weights are normal, with a mean of 173 and a standard deviation of 30. What is the probability? So as soon as we see this and we have that word normal, we know we're looking for an area under the curve, that a randomly selected man weighs more than 180. So we're looking for the probability that a one value from a normal is more than 180. Or if we wanted to draw this out, we know we're centered at 173 and we're interested in 180 or more. So if I was to do this question, I'd be using normal CDF because we're looking for an area under our normal curve. Lower bound of 180, upper bound of E99, mean of 173, and a standard deviation of 30. Which ends up being a probability of around 41%. Now, technically, this was not anything from part 7, right? This is straight out of part 5, straight off the last exam. Where we're going to see the stuff from part 7 is the next question. This one says, if 9 men are randomly selected, which means we've been given an N, say to be in an elevator, what is the probability that their average weight is more than 180? So again, we're looking for a probability, and there's a normal distribution going on behind the scenes. But just like in 6.1, we need to think about what we're looking for. And in this case, we're looking for the probability that our average from our sample is more than 180, which means I need a mean for that sample mean and a standard deviation for that sample mean, because that's what we're talking about, right? Average and randomly selected, we know this is all about a sample mean. This 180 in this case is not an X, but an X bar. So these are straight on that formula sheet like I showed you in the previous video. The mean of sample means is the original mean, so it's still going to be 173. And the standard deviation of a sample mean is the original standard deviation divided by the square root of n. So one thing to just kind of keep in mind here is if you're ever given a sample size in these normal questions, chances are you need to be dividing by that standard deviation by that square root. And that's the most common mistake students make on the test. Even if I give them the part A where I make them go figure out what the standard deviation is, they forget to use that new standard deviation when they go get the probability. So you almost want to cross out that original standard deviation once you get your new standard deviation. So this is still centered at 173, and we're still interested in 180 or higher. But this is going to change because when we go get this and use normal CDF, the only thing that will be different here is that standard deviation. Instead of 30, we're going to use 10. And this is where it would make a big difference if I was actually good about spacing out my graphs, because the standard deviation of 30 means that my first bunny hop is actually at 203. And then my so I did not draw my curve nearly wide enough, or I put 180 way too far away from 173. Whereas here, our standard deviation is 10, so our first bunny hop will be at 183, then 193, and then 203. So our entire distribution is a third as wide as our original distribution. So if we do this now out in our calculator, we get 0.2420. So almost half the probability of the previous one. And you can imagine here, it's a lot easier if you're just choosing one person at random to get someone who's over that threshold of 180. But in this case, we're looking at 9 people, and so we need all 9 of them, or at least the average, to be higher than that 180. So it's a lot harder to get that.